Okay, so in this video, we want to look at the derivation of the electric field inside a uniformly charged sphere. So our sphere is going to have a radius of r, and it's going to have a charge q distributed uniformly throughout. So you can think of the highlighter here is our uniform charge distribution, right? So the charge is uniformly distributed throughout the entire thing. And what we want to do is, right, so ignore the edges there that kind of bled over. But what we want to do is we want to know what the field is inside this sphere. So I'm going to draw a Gaussian surface inside here, okay? And let's recall what Gauss's law says. Gauss's law says that if I have some enclosed charge divided by the physical constant epsilon naught, that's going to be equal to the integral of the electric field multiplied by the surface area of the sphere. And this is technically a dot product, right? This is formally a dot product. And so what this means is that the field in my region of interest is going to be due, well, let's state it this way. I can calculate what the field is due to the contribution of the enclosed charge from this enclosed region. That is what Gauss's law implies. And you may be wondering, well, doesn't the charge in the outer region out here also play a role? And the answer is no, okay? The reasoning is somewhat similar for gravity. If you do an in-depth study of gravity, inside a massive body, whether it be a sphere, whether it be a spherical shell, whatever the case may be, if you're inside, whatever mass is enclosing you does not contribute to the gravitational field. Likewise, any amount of charged matter that encloses around you, especially if it's spherically symmetric, will not contribute to the electric field inside of an object. And it one way you can think of this is that electric field lines can't cross. Okay, so imagine, let's just imagine I had a spherical shell here, and this spherical shell had some charge on its surface, some charge Q. If the shell were charged, then I would have electric field lines, outside pointing outward, and inside I would have electric field lines pointing inward. But remember that electric field lines can't cross. So each of these field lines would be bending away from each other, but they can't really bend away from each other without crossing their neighbor. And so the result is that there's just simply no net electric field inside due to this shell. Okay? All of the electric field is exterior. So by the same token, there's no net electric field inside, and actually I didn't want to do that, I just wanted to erase this. There's no electric field inside the sphere due to any part of the sphere that is beyond our Gaussian sphere of interest. So what that means is there's just going to be there's just going to be electric field contributions from the enclosed region outward, okay? So that's the first thing we have to note. All right. Now, because that is the case, we really don't need to mess with the actual integral form of Gauss's law here. Because if our symmetry is spherical, we already know the electric field for a spherically symmetric charge distribution. It's just, right? And if we need to make this a vector, but the magnitude, right? The magnitude is just this. So we're more or less concerned with the magnitude for the moment, okay? So the field inside is going to be K times the charge enclosed by the sphere divided by the radius of our Gaussian sphere. I'm going to call that R squared. Okay? But what is Q enclosed? So Q enclosed is going to be found from the fact that the charge densities must be the same. Okay? So what that means is this. Our charge density, rho naught, is equal to, originally calculated from the entire sphere's charge, capital Q, divided by the volume of the entire sphere. Okay? But because the charge density is constant, the sphere is symmetrically charged, then that also means that the amount of enclosed charge from our Gaussian sphere, and I'm going to label our total sphere volume V, and our Gaussian sphere, I'm going to give it volume V prime. Okay? So these ratios must be the same. And so now this right here gives you a very easy way to calculate what Q enclosed must be in terms of the total charge, the volume of the entire sphere, and the volume of your Gaussian surface. And so Q enclosed is simply going to be Q times V prime divided by V. But V prime, okay, V prime is 4/3 pi r cubed, and V is 4/3 pi r cubed, capital R cubed, okay? And so this becomes 4/3 pi. I'm going to go ahead and put r cubed here and then capital Q over 4/3 pi r cubed, and the 4/3 and the pi's cancel out, and so Q enclosed is just Q times the Gaussian surface radius cubed over the radius of the entire sphere cubed. So then when we plug this in to our field inside the sphere, okay, we're going to have K times Q over R cubed over capital R cubed over R squared. But R squared is the radius of the Gaussian sphere, of the Gaussian surface. So because these two R's represent the same thing, they're the same quantity, I can cancel both of those out with two of these, and I'm left with one R. And so then I get K Q times little r over capital R cubed. So this is the field inside a uniformly charged sphere, okay? This is the field inside a uniformly charged sphere. And this is a linear relationship. If I plot field versus R, then this is a linear relationship until I get to the surface of the sphere. Okay? Until I get to the surface of the sphere. And at that point, this will drop off with a 1 over r squared dependence. Okay? Actually, technically, that should be lowercase r, because as I get outside the sphere, this is going to represent a Gaussian surface as well, something out here. We'll get a generic r. Okay, so outside the sphere, everything is just outward, like it normally is, 1 over r squared dependence, with this now being my new r. So we already know what the field out is. Okay, so that's the field outside the sphere, but inside the sphere it has this linear relationship. Your textbook actually then uses the definition of k, and remember that k is 1 over 4 pi epsilon naught, and so what happens is that the field inside the sphere becomes q r over 4 pi epsilon naught r cubed. Okay, so that is the field inside the sphere, right? It's your total charge divided by the ratio of your variable, your Gaussian radius, divided by the total radius cubed. Okay? So that is how you get that problem. You don't need any of these types of terms in your expression for this problem. Okay? You don't need any of that. It's purely this form inside. Okay?